Good afternoon, ladies and gentlemen. What a fascinating panel discussion. Straight from that into an inspirational talk. We have an action-packed schedule, and we're only halfway through day 3 here on the M42 main stage at the inaugural Abu Dhabi Global Healthcare Week, and so far it's been such a success. Now we are welcoming back on stage a friend of the stage. I could call him my co-host. I think he could be my co-host. Dr. Stephen Grogmeyer, please give him a big round of applause. He's infamous at Cleveland Clinic Abu Dhabi and has an amazing title, which I think I'm going to ask you to pronounce so I don't mispronounce it. But I have been learning the name of this session. It is Erysipelas to AI, leveraging the immune system to treat cancer. Did I get that pronunciation right?
Perfect.
So we have a wonderful audience amongst our AdNet community here, but also joining us online. So first of all, may we just define what we mean by erysipelas for me on stage, and then I know you have a wonderful presentation on this.
Yeah, so the use of the immune system to treat cancer is a very hot topic, and it's had a huge impact on the way we're able to treat patients that we never could before. So we're going to talk about erysipelas, which is a type of skin infection, and how the field of immune therapy for cancer actually started.
Fantastic. And may I just ask you to keep the mic all the way up so
Yes.
we capture all your brilliant words.
Yes.
And Dr. Stephen Grogmeyer, you of course are an Abu Dhabi resident and you enjoy the city here and mingling with the international and Emirati community that we have in Abu Dhabi.
Yes, it's one of the great aspects of living here is the diversity of the people that live and work in Abu Dhabi.
Fantastic, brilliant. And please do keep the mic warm.
Thank you.
Thank you so much.
Good afternoon, and I'm happy to be here. Today we're going to talk about cancer, and we're going to talk about the immune system. And we're going to go just briefly back to medical school, because to really understand how artificial intelligence can have an effect on improving the immune system for the treatment of cancer, we need just to review a little bit about how the immune system works, and we're going to do that. But first, we're going to just briefly mention about cancer. So we all know about cancer. There are many new treatments for cancer. Improvement in survival and outcomes of patients with cancer has never been better, but we obviously have a long way to go. We all know patients who've had cancer treatment and the treatment failed them. So this is really a look to the future. Cancer really starts with abnormal genes, and I need you to really lock in on this because it's going to become important later. Cancer starts with abnormal genes, and the job of a gene in a cell is to make proteins. And when you have abnormal genes, your cells make abnormal proteins that don't belong in the body. Okay, you got that? So some cancer cells have a lot of abnormal genes and they make a lot of abnormal proteins. Some cancer cells have a few abnormal genes and they make a few abnormal proteins. This is very, very important. So cancer cell, abnormal genes, a lot of abnormal proteins, a few mutations, a few abnormal proteins. So hold on to that because it's going to come back later. So not all cancer cells are the same. The next thing we need to focus on, going back to medical school, is the immune system. And the immune system is a very intricate and elegant system that keeps all of us alive. And the primary function of the immune system, historically and still, is to protect us from infection, bacteria and viruses. And the immune system is elegant in that it can specifically identify bacteria and viruses and other things that don't belong in our body. And it can mount a very specific attack against the enemy. And while it can be very effective in doing that, there's another side of the immune system which makes it not so good. And if the immune system is overactivated, it can also cause us a lot of problems. And an example of that would be ulcerative colitis or rheumatoid arthritis, where the immune system is overactivated and it causes inflammatory diseases that none of us want and are hard to treat. And at the very extreme, an overactive immune system can actually lead to a patient's demise. That's called septic shock. So it's very important, while the immune system is effective in treating foreign invaders, it also has to be controlled because it can cause problems. So you have that, Immune System 101 and Cancer 101. Now, how did the idea of ever using the immune system to treat cancer ever come about? It's a very interesting story, and I'm going to tell you the story. I'm going to take you back to about 1890 in New York City when a surgeon, and actually a surgeon did all this work, named William Coley, was working at New York Cancer Hospital, which is now it's the predecessor of what we now know as Memorial Sloan Kettering. Dr. Coley was a famous surgeon for a rare type of cancer called sarcoma. And sarcomas, even today, are extremely aggressive, difficult to treat, and often patients will succumb to sarcoma in spite of all the modern treatments that we have. So Dr. Coley was called to the hospital in New York to see a young lady who had a tumor in her hand. And it turned out to be a sarcoma. Well, at that time, the treatment for sarcoma, and still in some rare cases now, the treatment is actually to amputate the arm. And so that's what he did. And unfortunately, about 4 months after he did that, the patient developed spread of the cancer to the lung, and the patient passed away. So he got very frustrated by this idea of operating on people who were then subsequently going to pass away. So he said, we have to better understand the treatment of cancer and sarcoma. So he did then what any of us would do now. We went back and we did a study, and he did a study, and he looked at 90 patients treated for sarcoma at New York Hospital. And of the 90 patients, he found one patient in whom the sarcoma actually went away on its own. And so he started looking through the chart, and he couldn't really understand it, but it turned out that this patient who had a spontaneous regression of the sarcoma, his name was Fred Stein. He was a German man living in New York. He'd had 3 operations for recurrent sarcoma of the neck, but it turned out that spontaneously the sarcoma went away. And in reviewing the chart, he realized one thing that was present in Fred Stein's case that wasn't present in any other case. And that was the patient had a significant skin infection called Erysipelas. And he postulated that the immune response that his body made to take care of the skin infection also is what led to the regression of the sarcoma. So over the next 30 years, Dr. Coley expanded on this idea, and he actually started injecting patients with bacteria or parts of bacteria to treat cancer. And that remained in favor. He treated over 1,000 patients. He wrote many papers on this idea, but that was really the birth of the idea that we could use the immune system to treat cancer. And so what happened after that? The idea of injecting bacteria kind of went by the wayside, but interest in using the immune system didn't go away. And I'll fast forward a number of years to the 1970s. And this idea of stimulating the immune system not with bacteria, actually let me show you a picture first. This is actually a picture of Fred Stein. And so it turns out that Dr. Coley, after he realized that he had cancer regressed, he went down to Lower Manhattan and actually found him. And this is a picture of him 7 years after, a drawing of him 7 years after that skin infection. So again, suggesting that it works. But later on, as I was saying, the idea came that we would generally stimulate the immune system and treat cancer. So we were no longer injecting bacteria, but the idea came that we would inject stimulants of the immune system. And one of the known stimulants of the immune system is a class of molecules that's in all of us called interleukin. And so doctors in Washington, D.C. and other places started injecting patients with interleukin 2. Interleukin 2 is in all of us. And if you give somebody interleukin 2, it's a general stimulation of the immune system. And guess what? Some patients with very advanced or rare cancers, by stimulating their immune system with IL-2, were actually cured of their cancer. The problem was that some of the patients that I told you with this overactive immune response succumbed to the treatment. So that really didn't last very long either. It's still often used, or sometimes used in rare cases, but not generally regarded as a standard of care these days in the treatment of cancer. This idea of generally stimulating the immune system. So what's happened since then is a lot of progress in understanding the immune system. And this, we're going to go back to medical school. And I'm going to focus on one of the very important cells in the immune response called the T cell. And it was an understanding of how and what the T cell does that has really allowed us to advance in our use of the immune system to treat cancer. So on the slide, you see a picture of a T cell that's here. And T cell is a cell in all of our bodies. All of our bodies have many, 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 many thousands and millions of T cells floating around. And the job of the T cell, which has a receptor on it here, a little sensor on the surface of the cell, is to go around the body looking for things that don't belong. And the way it recognizes things is through this receptor. And let me go back, please. So if a T cell encounters a protein, which I'm showing here, a protein which doesn't fit into the receptor, there's nothing happens. So this means if the T cell is wandering around the body and doesn't see anything abnormal, nothing happens. If a T cell is floating around the body and finds something foreign that actually fits into the receptor, it stimulates an immune response, like we're all used to. If you have an infection in your body, a small infection in your body, the T cells find whatever shouldn't be there and they activate the immune response. And the point I want to make here is if you have a small amount of foreign body, you make a small immune response. So if you have a rose thorn on your hand, you have a small immune reaction. If you have significant pneumonia, you get very sick. Your body has a big immune response. So I show that here, and this is an important concept. So T cell sees 1 or 2 abnormal proteins, small response. T cell sees a bunch of abnormal proteins or abnormal material in the body, you get a big response, major immune response. Okay? So it was an understanding of T cells and how T cells work that revolutionized the way we use the immune system to treat cancer. And so in addition to understanding this about the T cell, what also is now understood is what controls or regulates the T cell. So it turns out that in all of our bodies, we have a system called the checkpoint system. And the checkpoint system is a group of receptors that allow cells to crosstalk. But what the checkpoint system does at baseline is keep everything quiescent. Because if we didn't keep everything quiescent, as I told you, you'd have a vigorous immune response and we'd all succumb to a lot of bad illness and overreaction of the immune system. So at baseline, the T cells are quiet. And then along came a group of medical doctors and researchers and scientists, one from the MD Anderson Cancer Center who recently won the Nobel Prize, Jim Ellison. And what Dr. Ellison won the Nobel Prize for was an understanding of this checkpoint system and what was keeping the T cells in a quiescent state. And they developed some drugs called checkpoint inhibitors, which you may have heard about. Checkpoint inhibitors are used every day in the clinic. Checkpoint inhibitors have saved thousands of lives around the world. And what checkpoint inhibitors do is they unleash the T cells to do their job. And sometimes the response to T cell therapy or immune checkpoint therapy is dramatic, and that's going to be shown here. So this goes back to 2015. It was published in the New England Journal, and it was one of the early documentation of the effect that these drugs could have on patients with very advanced or difficult to treat cancer. So this is a patient with skin cancer. Skin cancer, traditionally extremely difficult to treat. Most patients with skin cancer that was advanced in the history of cancer treatment succumb to the cancer. But this is a picture of a patient with advanced skin cancer. The patient was given 1 dose of these checkpoint inhibitors, which are the drugs which I told you which unlock the immune system, and the cancer went away completely. So now we have the ability to understand the immune system. We have drugs that can turn on the immune system, and we can treat cancer. Revolution in cancer treatment. One of the biggest advances in cancer treatment in my 20-year career of doing this. Very exciting, but it's not the only way we use the immune system. Another way we use the immune system you may have heard about is called CAR T therapy. So let me explain what that is. CAR T, again, T cells. To simplify this, CAR T cell therapy is when the T cells are taken out of a patient, they're modified in the lab, they're grown up, and they're put back into the patient. And this has also revolutionized the way we treat a lot of cancers. Especially hematologic malignancies are treated with CAR T therapy. So we take the T cells out, we modify them, we make them attack the cancer by adding certain molecules to their surface, and they're effective at treating the cancers. The last thing I want to mention before we start talking about artificial intelligence and what the future looks like is the idea of cancer vaccines. So if you go back to Cleveland, Ohio, a former colleague of mine named Vince Toohey, working in Cleveland, was also studying cancer and immune responses. And he realized in this example that there were certain breast cancers that actually expressed a protein. We talked about proteins before. And the protein was only expressed in breast cancer. So he came up with this idea that we could create a vaccine, or he could create a vaccine against that protein. And in 2012, 2013, he actually used the vaccine to treat breast cancer in mice very effectively. And over the last 12 years, progress in developing and using that vaccine has progressed significantly. And now, if you're a patient at risk for an aggressive form of breast cancer, you can go to USA at Cleveland Clinic in the main campus, and you might be eligible for a vaccine to actually prevent cancer. So patients in Cleveland who have hereditary risk for cancer can, in some cases, get on these trials, which are changing the way we not only treat but prevent cancer. So a lot to do with the immune system and the treatment of cancer, but when we look to the future, there's still some challenges. And while I told you all the success stories about treating cancer, many cancers can't be treated by current technology in the immune system. And let me explain to you why, and we're going to go back to what I told you at the beginning. Let me explain this to you. So, on this column, this is our checkpoint inhibition, okay? So, if it's red, that means the patient did not get checkpoint inhibition, okay? And then there's two types of tumors I told you about. We have tumors which have a lot of mutations and a lot of abnormal proteins. And we have tumors with a few mutations and a few abnormal proteins. So in cases, it doesn't matter what kind of cancer you have, if we don't give the immune checkpoint inhibitor, there's no response to, the cancer doesn't respond, okay? But it turns out if we give those drugs which stimulate the immune system, and that's shown in green here, so this is an example of a patient getting the drug that I told you about, where the immune system is stimulated, and the patient has a lot of mutations and a lot of abnormal proteins, and I told you the T cells are recognizing abnormal proteins. This is a perfect situation where immune therapy will work. And so an example of that is lung cancer, which historically is known to have a lot of mutations and a lot of abnormal proteins. It's why when we give an immune checkpoint inhibitor to a patient with lung cancer, often we see a profound response. We have the perfect situation. We've turned on the immune system. We have a cancer with a lot of mutations and a lot of abnormal proteins. And I told you the more proteins, the more vigorous the immune response. These are the patients that have a great response to immunotherapy. The ones that don't respond very well are here, which is a lot of cancers, where you give the immune checkpoint inhibition, you give the drug, the tumor has very few mutations and few abnormal proteins. Well, we need abnormal proteins coming from the cancer to mount an immune response. So in these cases, which is a lot of cancers, you give the immune checkpoint inhibitors, but the cancer doesn't respond. And one of the reasons is because, as I told you, a lot of cancers have a few mutations and a few abnormal proteins, so regardless of whether you stimulate the immune system, still no response to the cancer. This is where artificial intelligence is playing a role already and will continue into the future to helping us better use the immune system to treat cancer. And let me tell you about that. So there's three ways, at least three ways, that artificial intelligence can be used to improve the story. The first is simple. Most people here have heard of radiomics, so that's where you actually take a medical image, it's digitalized, and then all that information beyond what we can see is put into a computer. And there's a lot more information than our eyes can process. And what's happening now in radiomics is you take a computer and you analyze all the digital information, and you can then use that information to predict which patients will respond to immunotherapy and which won't. And that's very important because we didn't talk much about it, but these immune treatments can have a lot of side effects. And if the radiomics can tell us which patients will respond and which patients won't respond, then we'll give the treatment to those the immune therapy will help, and we won't give it to those it won't help. So that's the first way. The second way is actually getting back to this idea of the cancers with a few mutations and a few abnormal proteins, and that's shown here. So what now can be done is you take the genetic sequence of the mutations, the mutated genes in the cancer. The computer can now predict the structure of the protein that will be made by the abnormal gene. The computer can then predict which of those abnormal proteins your body would be most likely to mount an immune response to. And then what happens is you would immunize the patient with that abnormal protein. But without artificial intelligence, you could never figure out which of these small amount of abnormal proteins would be the best to immunize the patient against. So that's the second way. It's in helping us create vaccines against cancers without a lot of mutations. And that's happening. Trials are ongoing. And then finally is the idea, I talked about the T cell receptor. And the T cell receptor is that little flag on the top of the T cell. And it turns out another way to stimulate the immune system to attack the cancer is not to find the protein, but it's actually to reverse engineer the T cell receptor. So now you can use a computer. You know what abnormal proteins you need to immunize or you need the immune system to attack. The computer can now be used to actually generate in the laboratory T cell receptors that are expressed on the surface of the T cell, which are then given back to the patient. So you take the patient, you take the T cells out of the patient, you then put the new T cell on the cancers, on the T cells, and then you put the T cells back into the patient and you have a great response. So there's a lot of mysteries about why immunotherapy works and why it doesn't work, but artificial intelligence is definitely starting to and will continue to play a role in our ability to precisely control the immune system and the response of cancers to immune therapy. And this is important because we look to a future where most patients won't need to be treated with chemotherapy or less chemotherapy, and we'll use more of the immune system to help our patients be treated and recovered, and as I mentioned, even to prevent cancer. We're in a perfect environment to do a lot of this work, and I think we've heard a lot over the last 3 days about the outstanding artificial intelligence program that we have with our partners at M42, the National Biobank, the Genome Project, busy clinical practices here in the UAE, and a lot of need among our patients and patients around the world. So it's an exciting time, and hopefully we'll be able to come back in subsequent years and give you a further update on the progress we collectively have been able to make in leveraging the immune system to treat cancer. Thank you.
Allow you to leave the stage without a wonderful photograph. I remember that we did this together at Arab Health. We're going to have our main photographer here. And then I shall also take this opportunity to join you on stage and take a photograph as well. May I ask the photographer to return, because I want to commemorate this moment. Thank you so much.
Me too.
I introduced you as my co-host,
yes.
And I feel for the next exhibition we do need to make this happen. This has been such a wonderful event, and just a final note from yourself, in terms of in comparison to other health events that you attend, this is an amazing audience and a beautiful audience, I have to say.
Amazing, and the collaboration, seeing old friends, making new friends, and establishing new potential partnerships to change the way we're able to care for patients is very exciting.
Absolutely. And we began in your introduction by saying that Abu Dhabi in itself is a very special place. What's happening here, this nexus of health, sustainability, and technology, it's remarkable.
It absolutely is, and the burden's on us to take advantage of what's here, because we really are in a unique time and place, and if we work together, we can enact a lot of change.
And on that note, if we work together, we can make a lot of change. What an empowering note to end on. Ladies and gentlemen, Dr. Stephen Grogmeyer, please give him a big round of applause. Thank you. We're going to set the stage for a very fascinating panel discussion next. We're back in 2 minutes. Thank you.